Hello and welcome to this video on the rectangular waveform. The rectangular waveform is important because it occurs everywhere in life, whether we know it or not, and it's particularly interesting to scientists and engineers, again because it occurs everywhere. I'm going to begin by giving us some motivation as to why we should plow through the mathematics and try to understand what's going on. And the first one is, of course, making measurements. We'll take an example. We'll look at the Earth. The Earth has been around for a very long time, and because of that, it will have experienced tremors from its very inception, and of course, it continues to experience tremors. Now, when we think about the measurements of these tremors, they've only occurred they've started occurring very recently, and therefore the period of measurements certainly has had a beginning, a recent beginning, and every time we take a snapshot of our set of results and we analyze them, we have an end to that measurement period. So we have a beginning and we have an end, and outside the measurement time, of course, the signal can be considered as zero. So implicitly we've applied a rectangular waveform whether we realized it or not, and this of course has an impact on the results that we see, and we need to understand that if we are not to make misjudgments as to what we've actually measured. So that's an example of where the rectangular waveform occurs. There are other examples, of course. We have digital circuits in our computers, in our electronic systems, and digital circuits are driven by clocks, which are key, and clocks of course are rectangular in shape, and so we again must understand the behavior of rectangular waveforms and their properties to make sure that we understand what's happening in our circuits when things don't work. Analog circuits, of course, is yet another example. If we think about RF circuitry, we have mixers. Mixers are key to RF circuits, and mixers are driven by, of course, the data signal as well as the LO. LO standing for local oscillator. The local oscillator circuits basically switch differential transistors within the mixer, which chops our signal up and allows us to translate that signal from one frequency to another. So without going into the details of communications, what we can say is that the LO signal is a rectangular waveform, and the reason why we like to use rectangular waveforms is because we end up with circuits or solutions which give us the best noise performance compared to using sinusoidal waveforms to drive those blocks. And of course that's a positive. On the negative side, a square wave has harmonics, and these harmonics are troublesome. They are troublesome for digital circuits as well as analog circuits. So again, we need to understand the behavior of the rectangular waveform if we are to understand what's going on when things actually go wrong. So there's three very good motivations as to why we should understand rectangular waveforms. Just to give you further motivation actually on the mixers, for instance, I said that the harmonics are an issue. Well, people can get around these issues. In the case of mixers, people have designed things called harmonic reject mixers, and to do that you really had to understand the behavior of rectangular waveforms first before you could then play around with the mathematics to come up with solutions which could mitigate the issues with harmonics. Anyway, moving on, I'm going to give you one more example or one more point as a motivation point to go through the maths that is inevitably going to follow in these slides. And the fourth example is to do with sampling. So we talked about measurements and the measurements themselves being windowed, but of course when we sample a signal, the sampling will not be perfect. We will not have impulse sampling, for instance. A real circuit will have a finite time which it needs to capture the input signal, and the circuit that we use for that purpose is known as the sample and hold circuit, and that sample and hold circuit basically has a rectangular waveform function at its heart. So I've said a lot about why it's useful to understand this. Let's draw a rectangular waveform and basically define what we're going to be talking about throughout this video and possibly more than one video, because of course if this goes onto YouTube I need to break it down into smaller chunks. So this is a very bad drawing of a rectangular waveform, but hopefully you will get a picture of what I'm trying to show. Here we have just a couple of periods really to illustrate the rectangular waveform. We're going to label it now. So let's label this point as minus tau over 2, and this point here as plus tau over 2. And then the center point will be where time is equal to 0. So we've drawn the waveform to exist before time, which just out of interest should tell you that it's not physically realizable, but mathematically of course it will serve our purpose. We're going to define the period. We could have defined the period in different ways. Here we are centering everything around time equals 0. And we're going to say that the period is TP, so that's our definition of the period time. And this rectangular waveform will have a duty cycle, and that duty cycle is defined as tau over TP. We should label this waveform. So this waveform has two levels. It has an amplitude. We'll label A when it's on, and of course the other times it's 0. So let's label the x-axis. So we're talking about a time waveform, and we're going to analyze this waveform, convert it into the frequency domain using the analysis equation. I've gone through the analysis equation, by the way, in my set of videos on the Fourier series, so please watch those. It will make you feel comfortable with the mathematics that I'm going to go through next.